done with Paola Arias, Bastian Diaz, who is here, and also my students, Walter Rodriguez and Danilo Segarra. Okay, so everybody more or less agrees that the standard model needs to be expanded for many reasons, such as neutrino masses, the lack of dark matter candidate, the fact that we are all made of matter and there's no antimatter anywhere, and the typical problems with the Higgs being theoretically uncomfortable, right? So on this talk, I'll be trying to address the first two problems, okay? And I'm going to be working on models that address these two problems separately, not at the same time. And well, these models can all be tested, right? And there are many experiments that can probe for these solutions that you can try, of course, working at colliders, such as LHC, neutrino oscillation experiments, dark matter experiments, and so many others, right? You have, for example, the G-2 experiments. You have this now Atomkey experiment that's causing a stir. But today I'm going to focus mainly on collider experiments, okay? Now, the problem is that in all of this, not only in colliders, we haven't really found much, right? We talk a lot about there being, finding a desert, right? No signal of new physics at all. So then the next question is, why don't we find any new physics beyond the standard model? And well, this can be a very frustrating question, right? Because we have no idea why our expectations were so wrong. So we have to think, right? Why haven't we found anything? And one possibility is that this new physics could involve some signal that we did not expect at the LHC, right? One of such signals is that of long-lived particles, which are particles that have a very large lifetime, allowing them to travel a macroscopic distance before decaying. And this leads to non-standard signals, like the ones that you can find on this plot over here. So if a long-lived particle is produced in a collision, and it will travel a macroscopic distance, and then it will decay, right? So the decay products are called the non-prompt, and they are not associated to the primary vertex, okay? So in the typical example, you can have a neutral long-lived particle produced on the primary vertex that travels this distance and then decays within the inner detector, right? And then the decay products that can be charged will leave tracks, right? And from these tracks, you can reconstruct a secondary vertex, which is displaced from the primary. Okay, so this the appearance of these displaced vertices is one of the typical signatures of long-lived particles. I will not be talking anymore about this signal. In the following, I will concentrate on displaced photons, okay? Also called non-pointing photons. These are objects that are reconstructed entirely on the electromagnetic calorimeter. Okay, so you have the long-lived particle, it travels, and then it will decay entirely on the ecal. It will leave no signal on the inner detector, right? And these objects that are reconstructed as photons end up being delayed, right, with respect to a prompt photon, and they do not point towards a primary vertex, and that's why they are called non-pointing. Okay, so this is the main focus of this talk, the study of these non-pointing photons and how they can put bounds on models. Okay, so this is the overview. First, I will tell you more or less what this search is about. Then I'll give some technical details on how the search was recasted. And then I will put bounds on both the Dimension-5 Seesaw Portal and on the dark photon, dark matter model that I'm working with Bastian and Paola. So let's start with the search. Okay, what is this about? So as I mentioned, the photons coming from these long-lived particles take a long time to reach the calorimeter and do not point towards a primary vertex. And this is illustrated on this plot here, right? So here you have the interaction point, which is a place where everything is measured from. And here you have the primary vertex, the place where the proton-proton collision happened. Then from this collision, you have the long-lived particle that travels, and then it decays. In this particular example, it'll decay into a photon and some missing energy. In this example, it was a graviton. Then the photon will be detected on the electromagnetic calorimeter over here. As you can see, the electromagnetic calorimeter has got three colors or three patterns, which are meant to signify the three layers, right, of the electromagnetic calorimeter. And from this information, one can reconstruct the original photon path and then extrapolate back towards the beam line, okay? And from this information, one can notice that the photon apparently did not originate from the primary vertex. And this difference between these two positions is what is called the non-pointing parameter, delta Z gamma. Okay? So delta Z gamma, from when you have prompt particles, you would expect it naively to be 0. Of course, it's an experiment, so there will always be errors in the reconstruction. So delta Z gamma will have non-zero values, but they should be small. Okay? Now, why would we expect the non-pointing photon to be delayed? The fact is that a photon coming from the primary vertex will reach the electromagnetic calorimeter in a time determined by the speed of light, of course. Now, if you have a long-lived particle, this long-lived particle is massive, so it travels at a much smaller pace, right? So it'll be slower than a photon. And not only that, this distance that the long-lived particle and then the photon travel is longer than the straight line coming from the primary vertex, right? So we have slower particles involved and larger distances, meaning that the photon would arrive a couple nanoseconds later, okay, nanoseconds. The cool thing is that our experiments are sensitive enough to measure this, okay? And of course, naively, this delay would be 0, right? If the particle is prompt, experimentally, it will never be exactly 0. But if you have a long-lived particles, you would expect these two variables to be correlated. They should be both large for a long-lived particle. So that's more or less the idea of using the two of these for the analysis. So what does the search do? First, it triggers with an isolated lepton with large PT. Now, one would say, why would you trigger with an isolated lepton? We're talking about photons, right? So the point is that you don't want really to trigger with the photons, since the PT would have to be too large, right? So the idea is to do the trigger with an associated object. The idea here is to have the long-lived particle coming from the decay of the Higgs. Okay, so you would have the Higgs now being produced associated to something else, right? And this something else would decay into the leptons that would trigger the measurement. That's the idea, right? So you would produce the Higgs with a Z, with a W, or with a TT bar, and then the leptons would come from the decays of those particles. That's how you trigger. Then the Higgs would decay into the long-lived particles, and the long-lived particles would decay into the photon and the missing energy, whatever the missing energy might be. The problem with this is that the long-lived particles are not that heavy. They're at most 60 GeV or so, meaning that the final state photons are somewhat soft, right? And in addition, there's not that much missing energy. Okay, so you cannot put too stringent cuts on both the photons and the missing energy. So what does a search do? It takes at least one loose photon with PT larger than 10 GeV and some isolation criteria. Okay. Now the problem with doing this, of course, is that then you're flooded with background. So how do you cut this? You cut using the timing, you cut using the displacement, and you cut using your missing energy. So in order to do the measurement of the arrival time, you require one of the photons to be in the barrel region. Okay, this is the region where you have the best sensitivity to the arrival time. And if you have more than one, well, you use the one with the largest energy. And then another requirement is that you have this variable E cell larger than 10 GeV. E cell is the energy deposit. It's related to the energy deposit in the middle layer of the electromagnetic calorimeter. And the simulations done by Atlas determined that about between 20 and 50% of the total energy of the photon is deposited there. So then in order to measure the arrival time, you require this E cell to be larger than 10 G. Then you cut on the missing energy, demanding it to be larger than 50 GeV. And then you place your cuts on the arrival time and the non-pointing parameter, right? So the non-pointing parameter must be larger than 300 millimeters. And then the cut on yeah.
I'm sorry, one question about the trigger. Because if you have a set boson, in principle you can have electrons, muons, and taus, right? I mean, yeah. Which type of lepton do you use for the trigger exactly?
Sure. Here they use the electrons and the muons. They don't take into account the taus. Yeah, just electrons and the muons.
Okay.
It gets too complicated with the taus.
Yeah. Thanks.
Great. Thanks for the question. Probably they could do, I mean, the people in Atlas are great. They probably could do it with the taus, but they luckily decided to keep our lives simpler. Okay, so anyway, when placing the cuts on the arrival time, the people in Atlas distinguish between single photon samples where only one photon is measured with PT larger than 10 GeV, or multi-photon samples where you have 2 photons or more, with at least one of them on the barrel. If you have one on the end cap, it'll go into the multi-photon sample, but the analysis will be done on the one on the barrel. Okay, so you have these two cuts, and on the first one, you require the arrival time to be larger than 1.5 nanoseconds, and the other one 1 nanoseconds. And that was determined by Atlas, and we just followed. Okay, so what did we find? So these are the categories. You have the single photon category, you have the multi-photon category, And then you have a combination that is at least one photon, right? So the expectation was of 3.8 background events. They observed 4. In the multiphoton, the expectation was of 0.28 background events. No events were observed, and here 4.1 and 4. So of course we didn't see anything. So of course we're still frustrated. So what can we do with this? Well, we can put bounds on models, and this is what we are going to do in what's rest of the talk. So we're going to recast the search, focusing mainly on the 1+ category, right? We also did it for the 1 and the 2+, but let's stick with the 1+. Okay, so how did we do this recast? So in both models, we had exactly the same kind of behavior. We had the long-lived particle that would decay from the Higgs, and then the long-lived particle would decay into sorry, I said something correctly. The long-lived particle would be produced from the decay of the Higgs, and then it would decay into a photon and missing energy. In both models, we have the same thing. Okay. We of course considered ZH, WH, TT bar H modes. We implemented the models in fine rules, then generated events in MATGRAPH. We performed the shower and hadronization in Pythia, which returned the HEPMC output. And the typical thing to do here is to put the HEPMC into Delphis. We had an intermediate step, right? We took the HEPMC output and we reconstructed the long-lived parameters for the photons, right? We used the truth level information and calculated the time delay and the delta Z gamma. For the time delay, it was easy, right? We have the PT of the long-lived particle, right? We have the position where the long-lived particle decays. So then we have the time, right, that it took this long-lived particle to travel from the interaction point, from the primary vertex to the place where it decayed, right? And then we have the photon that travels at the speed of light, and from the PT we have the direction, right? And from that we can calculate the time it takes for it to reach the electromagnetic calorimeter. Very straightforward. We repeated this for prompt photons, right, as a function of pseudo-rapidity. And with this, we managed to calculate the time delay. Very straightforward. For the non-pointing variable, things got a bit more complicated because ATLAS uses a 2D projection of the photon trajectory, right? So it does not use the azimuthal angle. It only uses the RZ information, okay? So what does it do? You have the photon entering the first layer and then the second layer of the calorimeter, and then it determines the Z coordinate in R1 and R2, right? Here you have R1 and R2. So if you know R1 and R2, you can calculate what is the Z coordinate of the photon at each one of these points. And then you can calculate this delta Z gamma. The problem is knowing what is R1 and what is R2, because it turns out that R1 and R2 are not fixed. They are functions of the pseudo-rapidity, right? So this is the first layer, and this is the second layer, right? And this is the pseudo-rapidity, right? So as the pseudo-rapidity changes, the position of these R's change. So for R1, the change is not very strong, but for R2, you do get a difference, okay? So that's the point. We had to take into account this information. So we determined the pseudo-rapidity for the photon as it entered the calorimeter, and then for that value of pseudo-rapidity, we determined R1 and R2. Then we continued the trajectory of the photon, and then with this we calculated delta Z. The final formula is horrible. It's here, right? I just put it there for completeness because the idea I've already explained, right? But this is the formula that one has to use to get delta Z gamma. Okay, so now we have the time delay and we have delta Z gamma. So all of this is repackaged on the HEP-MC and processed by Delphis. And I'm not going to tell you the whole thing that we did with Delphis and the analysis, okay? For this, you can see the paper, or you can ask me at the question time, right? But it was a lot of work. It was a lot of work. And if we review all of this work, then we're not going to have the time, okay, to look at the conclusions. All right, so let's go into the models. The first model that we looked at was the Dimension-5 Seesaw Portal. That was the original motivation for going into this analysis. So probably most of you know about the seesaw mechanism. The seesaw mechanism is most likely the simplest way of giving masses to the standard model neutrinos. What one does is you add right-handed neutrinos, and then from this you add all of the possible couplings. So what are the possible couplings? You have the Yukawa coupling and the Majorana mass. Okay? Then after electroweak symmetry breaking, the mass matrix acquires this shape, right? With MD being proportional to the Yukawas that I mentioned before. And then when you diagonalize this mass matrix, you get the light neutrino masses having this structure, right? So in this kind of setup, the smallness of the light neutrinos, of the light neutrino masses, would be explained by the heaviness of the heavy neutrino. Going a little bit more into detail, once you have your 6x6 mass matrix, you have to diagonalize it, leading to a mixing matrix. And this mixing matrix has got an active light sector, an active heavy sector, a sterile light sector, and a sterile heavy sector. Right? So here you have to distinguish between the interaction states, which are the ones that appear originally in the Lagrangian, where you have the active and the sterile neutrinos. And then you have to distinguish those from the mass states, which are the ones that come out from the diagonalization of the mass matrix. And here you have the light neutrinos and the heavy neutrinos. So you have active sterile and you have light heavy, right? So then the mixing matrix gives you that, the active heavy mixing, for example. Right? So this mixing matrix is crucial, right? Because it turns out that the heavy states are not sterile. They're mostly sterile, but they're not sterile. They can interact, the heavy states can interact with the W and the Z via the mixing, okay? So here you can see a typical process for studying these heavy neutrinos. You can produce them via a W, right, which produces a charged lepton and a heavy neutrino via the active heavy mixing. And then this heavy neutrino can decay again via an active heavy mixing into a charged lepton and a W, which can be on shell or off shell, depending where you are, which then splits up into a lepton and neutrino. So these mixings are very important. Okay? Unfortunately, these mixings in the strict seesaw limit are very small. So one would expect this to be small, making them hard to find at colliders. one can play with the textures of the mass matrix, making them large, but the naive expectation is that this should be small. Now, in this talk, I'm not really working on the standard seesaw because the neutrinos, being neutral, do not couple directly to photons. However, you can extend the type 1 seesaw with dimension-5 operators. Okay? These dimension-5 operators include only the sterile neutrinos. Okay? So you have to add these two operators here that have got the sterile neutrinos, and this one has got the Higgs, and this one has got the B mu nu tensor. Okay? So you have two new couplings, alpha and phi and alpha and B, giving you these interactions. This time, the active heavy mixing is not the most important one, because these interactions involve the sterile states, not the active states. So now you're interested in the sterile light mixing and the sterile heavy mixing. Okay? The sterile heavy mixing will be large, the sterile light mixing will be very small. Okay? So what interactions do you have? Well, here you see you have the interaction of two fermions and two Higgses. If one of them acquires a VEV, then you can have the decay of the Higgs into two fermions. And this one here involves two sterile neutrinos, which must be of different families, different generations, and B mu nu implying an interaction with a photon or a Z. In particular, you can have this interaction here that leads to this vertex. So the N4 will be able to decay into a light neutrino and a photon via this dipole operator that depends on this alpha n.
Joel,
okay.
Can I
Yes.
interrupt you? Well, so how many right-handed neutrinos are you introducing?
In this case, two. You need at least two heavy ones to have this operator present. If you have only one, then there are some antisymmetric requirements here that make this operator vanish. So you need at least two heavy neutrinos.
Okay. And I didn't understand very well the motivation to include this higher order operator. I mean, if we neglect the second row, we just keep the first line. You say that in principle you can have long-lived particles, but they are too suppressed. Is that right?
Yeah. Okay. So what happens is that if you have this term, this dipole term in particular, in the regions where you could have long-lived heavy neutrinos, okay, this operator usually is the one that dominates. Well, it depends on the value of alpha, of course, no? But this kind of operator would dominate, and it would invalidate all of the previous searches involving long-lived heavy neutrinos. Because a branching ratio in the standard channels would be 0. Well, very small.
But just to understand the simplest scenario with the standard model without extra operators. So I mean the first line, and in the previous slide you showed this production via W's, and then the W's emitting these right-handed neutrinos. What about that specific framework in the long-lived particle?
Yeah, there's no problem. No. A lot of searches have been done on the standard on the standard seesaw, right? A lot of searches have been done, and it's perfectly fine. It's perfectly fine to have them. The issue is if these mixings are on the seesaw limit, then it will take a very long time for us to be able to probe that region of the parameter space. To be able to probe this process, you need to enhance these mixings, which is perfectly normal. It can be done. You have to justify it a little bit, but it's not a problem. It's not a big problem.
Okay.
And it's perfectly fine. You can do that. You can do that.
Okay, and additionally, the first effective operator that you are considering with this the Higgs doublet coupled to the sterile neutrinos, is the idea of that operator is to enhance the production of the right-handed of the sterile neutrinos via the Higgs decay, right?
So from this operator here, you can have the Higgs decaying into a heavy neutrino and a light neutrino.
Right.
If you want the Higgs to decay into two heavy neutrinos, then it's complicated. Okay, it is suppressed. But furthermore, if you want this UAH to be small enough such that you have long-lived particles, then the branching ratio of Higgs going into a heavy neutrino and light neutrino becomes very small. So asking for a long-lived particle will suppress its production.
Okay.
The advantage of going to dimension 5 is that you have two operators, one which we will associate to production and the other one which we will associate to decay.
Okay, perfect.
Yeah, I mean the main idea is to have to be able to probe this model with the search I have just mentioned. That's the main motivation. And the fact that we haven't seen anything, right? So maybe the reason we haven't seen anything is that we have been looking for this kind of processes, and maybe the one that dominates is the one ruled by this operator. Maybe, right? So you have to keep on looking.
And just my last question is regarding the first effective operator. Once the Higgs get the vacuum expectation value, would you have here a kind of Majorana mass contribution to the second term in the first line?
Exactly. Thank you very much for that question. Yeah, of course you do. Of course you do. So you have to be very careful, right? Because you have two contributions to the Majorana masses, right? Of course, if you use the Casas-Ibarra parametrization, you can get whatever mass you want. However, you have to be careful, because in order to get that mass, you might be having a cancellation between this MR and this other coefficient here. Fortunately, we checked and we don't have it. But in some regions of the parameter space, you could have some fine-tuning by demanding that the heavy neutrino mass has got some value.
Okay. It's not that trivial. Okay.
It's not trivial. It's not. That's why it took us 2 papers to control this model.
Okay. Thank you.
Yeah. Okay. So thank you very much for the question. So that's the idea, right? We have these 2 operators, and the whole collider phenomenology will be dominated by these 2. Okay. With a contribution from the mixing, of course. Okay, so this is the idea. We'll be producing this heavy neutrino, and then this one will be decaying into a light one and a photon. And since this goes through a sterile light mixing, then this width is suppressed, allowing the heavy neutrino to be a long-lived particle. Okay, that's it. So then what's going to happen? We're going to have the proton-proton collision producing a Higgs. Then the Higgs will decay into an N4 and an N5. I can tell you later why we are choosing this production mode. The N5 is not long-lived, so it decays into an N4 and a prompt photon, okay? And then you have the two N4s being long-lived, traveling their macroscopic distance and decaying each into a light neutrino and a photon. And these two photons are displaced, okay? So we generated events for this model, and we were able to place bounds, right? And bounds on what? Our bounds were placed on the branching ratio of Higgs going into N4 and N5. Okay, so that's the bound that we can put. So this is what we have. This is our main result. Okay, so here we have M4, the heavy neutrino mass. Here we have alpha NB, which is our coupling to the photons. Okay, so the smaller this is, the more long-lived the heavy neutrino is. And these curves give you the maximum possible value of the branching ratio of Higgs going to N4 and 5. So for instance, in this region, the branching ratio cannot be larger than 2%. Here, 8%. Here, 20%. And over here, you have no bounds. Okay, so outside of this region, the displaced photon surge is not sensitive. In colors, you have the lifetime, right? Just to give you an idea, the ideal lifetime, the decay length is of about 1 meter, right? You see more or less here, the 1 meter is where the largest sensitivity is, more or less. This can be, oh, sorry, let me explain why they have this shape. So here, for large alpha and B, you lose sensitivity, okay, because you have a large coupling, so the N4 is not long-lived, and the photon is prompt. Okay. Over here, you have a very small alpha and B, so the heavy neutrino is too long-lived, and it escapes the detector. It decays outside the detector, so you're not measuring any photons there. In this region is where the sensitivity is best, right? So it's a region where the masses are large. Okay, so why do you want larger masses? The reason is that the heavy neutrino is slower, right? The amount of energy is the same, right? But it's got larger mass, so then its momentum is smaller. It moves more slowly, so then the photon is more delayed. Okay, so the delay time is larger. In addition, since it is moving slower, the photon and the light neutrino will be less collimated, right? The faster it goes, the more collimated its decay products. So if it's slower, it'll be less collimated, and the photon will have a larger non-pointing parameter, right? If it's collimated, it will point towards the primary vertex. And finally, in this region over here, alpha and B is small, and the standard seesaw decays start to dominate. So the branching ratio for heavy neutrino going into a light neutrino and a photon is no longer 1. Okay, so you lose sensitivity again. So this is the reason why you have this region with this shape. And if you can translate this in terms of the other parameter, which has to be of order 10 to the minus 5, right? More or less. 2 times 10 to the minus 5, 4 times 10 to the minus 5, 10 times 10 to the minus 5. Okay, I'm running out of time, so let's move on to the second model. which is work in progress. So hopefully I'll be faster. Okay, so having finished this with the neutrinos, we were looking for other models that could help us with dark matter. I had a small introduction to dark matter, but I think I'll skip it due to time constraints, right? But you all have heard about thermal dark matter and the WIMPs, giving you freeze out, and non-thermal dark matter with FIMPs, which is produced via freeze in. Okay. So having finished the work with the heavy neutrinos, we're starting to look at some other models that could be probed. And then we started conversations with Bastian and now with Paola. Our idea was to have a similar model where the Higgs would decay into two long-lived particles, and each long-lived particle would decay into a photon. And now, instead of a light neutrino, it would decay into a dark matter candidate. And the inspiration came from the dark axion models, right? Developed in these papers here, giving you this kind of couplings. In particular, the second coupling was super interesting, where you had a dark axion which would decay into a photon and a dark photon, okay, which is exactly the same thing that we had on the previous work. This dark axion would be considered the long-lived particle, and the dark photon would be considered the missing energy. Okay, so that's what we decided to work on, to look for a model that could be probed by these displaced photons and could give you dark matter. Now, if we were going to get this dark photon to be the dark matter candidate, we would want it to be stable, okay, or at least very long-lived. So what we did is we added a Z2 symmetry, under which the photon would be odd, the dark photon, sorry, would be odd, and this this dark axion, which will not be a dark axion, okay, but at that point it was a dark axion, would also be odd. Okay, this dark axion would not transform under the U1 symmetry of the dark photon, so the only coupling would be this one. Okay, an effective coupling with the dark axion, the dark photon, and the B mu. Okay. As you can see, since this got the tilde, this is not really a scalar, this is a pseudo-scalar, since it's supposed to be a dark axion. But then we said, okay, what we need is for this axion to be produced from Higgs decays. Okay, so then we added the interaction term for the dark axion and the Higgs, which is this one, this lambda HS. The problem is that in axion models, this lambda HS needs to be very small or vanishing, right? Because there are no derivatives here. And in our searches, we actually want this lambda to be large, right? This is the thing that we are constraining, right? So then we said, okay, we have to be honest. There might be some models where this could be an axion, but we're going to get in trouble if we start calling this an axion, right? So then we said, okay, let's call this dark photon with a scalar portal. And in principle, there exist works where this lambda can be large and this is still an axion, okay? But what we're going to do is we're going to consider this a dark photon, dark matter model with a scalar portal. And then our objective is to put bounds and check if you can get the correct relic density. This time, for this work, we added an additional constraint and we compared the bound coming from the displaced photon and Higgs invisible decays. Okay, we use this bound coming from Atlas, right? So in principle, the long-lived particle can escape the detector, and we saw that in the region of parameter space, it did escape the detector. So then we said, okay, in these regions, probably the displaced photon is not so good. We could look at Higgs invisible decay. So we implemented this, right? And we demanded the branching ratio of Higgs to invisible to be smaller than 10% or so. These are our preliminary results. This is the limit on the branching ratio of Higgs going into the two scalars versus the lifetime, well, the decay length, okay? For two benchmark scenarios. The first one, where you have a mass of 60 GeV and your dark photon has a mass of 1 GeV, and the other one where the scalar has got a mass of 30 GeV and the dark photon has got a mass of 1 GeV. So these are the bounds, these two, coming from that displaced photon search. As you can see, the 60,1 scenario is the best one, allowing us to put bounds on the branching ratio smaller than 1%. So we're very happy with this. For the 30%, for the 30,1 case, you had a bounds under 10%, which is also quite nice. The dashed lines give you the constraints coming from Higgs to invisible searches. As you can see, these searches are most sensitive when the decay length is very large, right? Meaning that the most likely thing is that the photon will decay outside the detector. And when the decay length is small, of the order of 1 meter, then it's unlikely it will decay that, outside the detector, and then the sensitivity drops. Okay. Finally, the shaded region is a result of a fit done some years ago by Atlas for, involving Higgs decays to undetected final states. What they did was a fit involving several states they detected, and then they said, well, there is a possibility that the Higgs was decaying into something else that was not included in this fit, and this cannot have a branching ratio larger than about 11%. Okay, so that's what the shaded region is. So what we see is that if you have a very long decay length, then Higgs to invisible is the most sensitive probe. If you have a very small decay length, then the fit result is the best. And then in the in-between, for decay lengths between, say, 50 centimeters over to 100 meters or so, then the displaced photon is the best, is the most sensitive for the 60,1 case. This can also be expressed in terms of lambda and G. So remember, lambda is a coupling to the Higgs. G is a decay of the scalar to the dark photon and the photon. So now we see that our searches are sensitive to values of GD over lambda smaller than 10 to the minus 9 or 10 to the minus 10 or so. Okay? And you can bound lambda down to the order of 10 to the minus 3.
Joel?
Yes.
One thing is that we are using GD as the inverse of the cutoff lambda. So,
yes. Oh, sorry. Yes, it should be GD. Yes, this is a notation problem. Sorry. Okay. You're right. You told me about this some months ago, and I forgot. You're correct. Because we have. Oh, no, I'm consistent. Yes. Okay, so I'm not consistent with the paper, but my plots are consistent with myself. Good. Sorry.
Yeah, the Wilson coefficient that we are considering in principle is equal to 1, I guess.
Yeah.
Basically, GD is equal to 1 over lambda.
Yes. So at least I'm consistent with myself. So the GD that we're going to use on the paper is equal to the GD over lambda in my presentation. Yeah, sorry. Yeah, I forgot about this. You corrected me and then I forgot. Okay, here we go. Yeah, but I'm being consistent. Yay. So the ones that we're using are of the order of 10 to the minus 10 or so, and the bounds that we can put on lambda are of the order 10 to the minus 3 or so. Okay, so with this in mind, then we can say, all right, what is happening with dark matter, right? What are the implications of this for dark matter? So first of all, with this GD over lambda, now I made the mistake of not putting the lambda. So since the GD is so small, then the dark photon is a fib, okay? It's very feebly coupled. The scalar, well, I would call it a WIMP, since the lambdas are large-ish, okay? So it can be thermal or not, depending on the exact value of lambda, okay? So thus, we are led to freezing production of this dark photon, dark matter, with possible thermal phi. Now, if you just plug this in, you overproduce dark matter if your reheating temperature is large, right? So what this says is that this kind of search would probe this dark matter model if it is in the context of a cosmology with a low reheating temperature, okay? So this is what we have. Now, in that case, which are the processes of interest? I'm about to finish. We started like 10 minutes late, right? So it should be okay. So the processes of interest. Yeah, thank you. Great. I'm about to finish. Don't worry. So the processes of interest are mainly these two. So you have an exclusive 5 production, right? Where you have two particles in the thermal bath that produce an off-shell Higgs, which then splits into two scalars, right? And this is also the relevant process to determine if the scalar is thermal or not. And then on the other hand, you have the same, the standard model particles that produce a phi and a dark photon through an off-shell gamma or Z featuring GD. Okay, now I'm putting GD instead of GD over lambda. That's a shame. Okay. Anyway, if you have enough phi being produced, then you can also get a dark photon being generated via the phi decay. Okay, and this phi decay can be late or so. So let me give you a couple of examples, which were very kindly provided by Bastian last week for this talk. So here you have a scenario where the mass is 30 GeV, then the dark photon is 1 GeV. This GD, now it should be GD over lambda, is 10 to the minus 12, okay? So the decay length is of 1,000 kilometers, right? So this cannot be probed by us, right? But it's still instructive. So in this case, you can follow the gray solid line, which is the yield for phi, for the scalar. As you can see, it is thermal here. Lambda is 10 to the minus 1. So it is thermal. It will go through freeze out. It'll leave for some time, and then it'll decay, boom, and the yield will go down. At the same time, this curve in black is the yield of the dark photon. It is produced via freeze-in, and then it reaches a stable value, and then it starts increasing. And the reason it increases is because the scalar is decaying into dark photon. So this increases the yield. Okay, and you can have the same thing for other values of lambda. For smaller lambda, here you see 10 to the minus 3, the scalar never reaches thermal equilibrium, but still it has got a freezing production, it lives a little bit and then decays. If you have a larger GD over lambda, then such as the one that can be probed by us, so 5 times 10 to the minus 10, with a decay length of 4 meters, then here the associated phi gamma production is the one that dominates. So here you see that the photon yield is produced via freeze-in, and then it stays the same. Right? You also produce some scalars, but then by the time that they're decaying, look, they decay before they freeze out. They never freeze out, they decay before that. Their yield is so small that they do not contribute to the dark photon yield. So this is what we expect will be the standard thing in our results, right? These are all preliminary. So then you can do a scatter plot, right? In the GD over M5, this is, okay, GD over M5 parameter space. And all of these points will give you the correct relic density, right? With different, okay, let's not pay attention to this at the moment. These colors over here will give you the value of lambda HS necessary to give you the correct relic density, okay, around the parameter space. And this should be compared with our results for displaced photon searches. So on the same plane, you can rule out lambda HS of the order 10 to the minus 3, 2 times 10 to the minus 3, over here around 10 to the minus 2. Okay? So if we put these two things together, which will be done in our final results on the paper, we find out that we can put constraints on more or less this region of the parameter space. Okay? So this means that all values of lambda over 10 to the minus 2, that means everything here that is colored green, yellow, orange, and red is ruled out by the displaced photon search. This means that you can produce a relic density and be ruled out by these searches, right? So these searches are indeed sensitive to dark matter models, okay? Dark matter models with low reheating temperatures and this funny thing of this Z2 symmetry with the photon, but it can be done. So that's the point that we want to transmit over here. Okay, so the take-home messages, I hope you enjoyed this talk, but what we want to emphasize is that the searches for displaced photons can indeed place bounds on models with long-lived particles decaying into photons and missing energy. The best sensitivity is for decay lengths of 1 meter. If you have larger lifetimes, then you'd better go to Higgs to invisibles. If you have smaller ones, then the fit is better. If you go into the Seesaw Portal, then you can put strong bounds on the effective operators of the order of 10 to the minus 5 inverse GeV. And in the context of these dark photon dark matter models with the scalar portal, the bound is of the order of 10 to the minus 3, right? Now, these preliminary results are very promising. We see that for low reheating temperatures, you can indeed reproduce the correct relic density and be constrained by searches at colliders. So please stay tuned. This paper will be coming out very soon. Thank you very much.
Thank you so much, Joel, for the very nice and very complete talk. Joel,
yes.
I had a question regarding this. Can you please remind me why the bound for is about 10 to the minus 3 for this frontal coupling? What happens is larger values are taken?
Right. So this is the same thing, right? So if you have no, sorry, for lambda, you mean lambda or
exactly.
G?
Lambda is
Okay, lambda. So this is the maximum value of lambda. If you have a lambda that is larger, then the branching ratio of Higgs into two scalars will be larger. So you would have more non-pointing events than the ones that your search allows.
I see. Thank you.
Yeah.
Bastian, do you have questions?
I have always questions. Well, according to this plot in the right, those are not the final results with respect to those contours, right?
Yeah. So the next thing that is happening is so these contours are only they only correspond to the displaced photon searches. We have not included the contours for invisible Higgs decays. So the thing is that my students brought me the combined plot and I didn't understand it. So I asked them to do the plot separately and then we'll put them together, right? So in principle, there will be what we expect is that we will be able to probe this region of the parameter space too.
Yeah, okay. So
with couplings of the order 10 to the minus 2, right? Also. So all of the red, yellow points here, I think we will be able to rule them out too.
Okay.
But we need to I need to understand the plots. And this region here is much more complicated. I think this one is beyond what we can hope for.
I see. Okay.
Joel, what about the constraints from direct detection, or they are irrelevant in that case?
From direct detection, you mean in dark matter?
Yes, in that model with the dark photon.
I don't. I mean, I'm not really an expert. Probably Bastian can say much more accurate things than I can. But I would expect that since you have a GD of order 10 to the coupling is of order 10 to the minus 10, I do not think that you can have any possibility of having direct or indirect detection of these things.
Yes, it will be very tiny, very surprised.
If to test this parameter space at direct or indirect detection, right?
Mm-hmm. I don't think it's possible.
Yeah, it seems that it's not possible in principle, considering that GDs, yeah, as Joel said, it's too small.
I mean, any interaction will have GD squared, right? So the coupling is 10 to the minus 20. So I would be very surprised if somebody told me that this could be probed.
No, it will not be probing neither with the filter sensitivity. Impossible.
Yeah.
At least for direct detection.
And for this scalar portal, I suppose that the bound that you are taking with the Higgs doublet is very small, so very small deviation from alignment limit.
Sorry, what's that again?
For this scalar portal phi, you are considering very small missing angle with the Higgs doublet. So in principle, deviation from alignment limit will be too small. Will be mostly the scenario will be mostly alignment of the standard model.
There is no scalar mixing.
No scalar mixing.
No, because so you have this funny thing of the phi having the Z2 symmetry.
I see.
Right, and it's unbroken. This one does not acquire a VEV.
I see. Thank you.
Right, we have to assume that there is a dark air sector giving masses to the dark photon, right? Which at the same time will also lead to this effective operator. But we didn't want to get into this ultraviolet completion thing, as it would turn out very messy, probably.
Thank you.
Yeah.
See. Bastian, do you have more questions?
I'm fine.
Thank you so much, Joel, for the very nice seminar. Very nice seminar. Today, I think
Thank you very much.
internet problem at the university, so maybe that's why this is the reason why people didn't connect it. Because when I arrived at the university, some person from the system, he told me that there were some internet connection problems. Some colleagues were having connection problems. It happened just today.
Ah, it's a shame.
It's a shame. So I think that's why very few people connected despite I announced the seminar. I announced it on Friday. Usually in the seminar, around 10 people connect, sometimes more, but today have been completely different people.
It's okay. Is this being recorded?
Yeah, it has been recorded. So we have a YouTube channel. So people can at least get it. But if it's okay for you, maybe I will wait because you told about some work that is in progress. If you prefer that I upload the tool after you put your past paper in Arcade, I can wait to upload it later, as you prefer.
Yeah, it can be Bastian next time.
So you prefer, Bastian? If you want that I wait until the paper is in Arcade, I can upload it all in YouTube later.
I cannot hear you very well. I feel something in the background when you.
No, that usually the seminar are recorded, but I noticed that the second part of the talk of your talk was about work in progress. So if you prefer that I upload the talk later after you put the paper on archive, I can wait to upload it later. Or if for you it's not problem that I upload it, for example, between the next few days, I can upload it between the next few days.
Yeah, or it could be Lucia, or it could be any of the students. Actually, the students would profit from that.
The student will, you say?
Would profit. No, it would be advantageous for them to have a talk.
I will do better for him to have the to this upload it before the same link, or to upload it later.
Sorry?
You mentioned that your student will be.
So when